Good afternoon, everyone. I am Mr. Ish. Thank you for watching this video, and I appreciate everyone out there watching my videos, learning from me what I have learned through others. Today we will look at this topic on integrating by parts. I've already presented a overview video on this. Today we're just looking at practice questions of integrating by parts, and the more you do, the easier this procedure gets. When we look at the practice questions in today's video on this integration by parts technique, we'll be looking more so on definite integral type questions. For our first question, we look at this. We have this x cosine x dx from a lower limit of 0 and upper limit pi over 2. These are all questions I've just taken out from my textbook here on Calculus. And you have two different functions over here which are not related by means of a function and its derivative. So polynomial substitution technique is out, leaving you behind this excellent technique to utilize. The best thing you can do over here, and this is the format we're always using, is to make good substitution here for u should be here x, because that'll eliminate that. Once you do its derivative, it will eliminate that variable. Du is equal to the derivative of x, which is just dx. V is always equal to the integral of that which remains within your integrand, which here is integral cosine x, and you know that to be sine x. A good technique over here with regards to definite integrals is don't worry about them, at least until the end, and proceed as if you didn't really see them to begin with. Put everything here in this uv minus integral v du format. Don't confuse the u's with the v's or the v's for the u's. U here is x, v here is sine x, minus integral v sine x, du is dx. And this is what you can do. You can just go like this and put pi over 2 and 0. Generally, you can get away with this little modification here, and you can proceed from here. This is very easy to do. You'll have x sine x minus integral of sine x is a minus cosine x, which affects this minus and makes it a positive, and you end up getting cosine x. There's no need to put a plus c because we have definite integration. Here you have to put pi over 2 upper limit and 0 the lower limit. A good way to look at all of this is just pi over 2 sine pi over 2 plus cosine pi over 2. That's the upper limit placed in, and then minus everything here with the lower limit 0 sine 0 plus cosine 0, and you can evaluate this way, and this is how you should ideally look at all of these. Sine pi over 2 is just a 1, pi over 2 times I1 is a pi over 2, cosine pi over 2 is a 0 plus 0 minus this zeroes out, cosine 0 is just a 1, which affects with this minus, and you get a minus 1. So essentially you have pi over 2 minus 1, which will lead you to your final answer, and we'll calculate that for you. You can use a calculator here. Pi divided by 2 minus 1, and the answer to this question will be 0.5707. And what will this 0.507 represent? It will represent, if you were to graph this, the area below the curve from an interval 0 to pi over 2. Let's look at this question. We have an integral lower limit 0, upper limit pi over 6. We have sine x tan x dx. What if you were to use some substitution technique rather than substitution by parts or integrating by parts? What will happen? And I will show you. If you were to ignore the intervals and just look at sine x tan x dx, tan x is equivalent to sine x over cosine x. You could essentially combine everything. You'd have sine square x over cosine x dx. Let's pretend we can use polynomial substitution technique. U is equal to sine x, du is equal to cosine x dx, dx is equal to du over cosine x, and see what happens. You have u squared here coming in place of sine x because sine x is u. You have over cosine x, and you have du over cosine x, and you end up getting u square over cosine square x du, and you have two different variables, one in terms of u, one in terms of x, and you have not gotten anywhere, which shows you that this question right here should have been handled another way. The most logical way to handle this question is by integrating by parts technique, uv minus integral v du. The most challenging part over here is what this initial u will be. If you make u is equal to sine x and you proceed with there, you'll end up getting into trouble because the question, your initial integrand will become harder the next step. If you make your initial u substitution tan x, everything will become more easy and you will see it, and this is the route we will take. U is equal to tan x, du is equal to secant square x, v is equal to the integral of what remains sine x dx, which is minus cosine x. Everything comes into this format right here, uv minus integral v du, and u here is tan x, v here is cosine x, but you have a minus coming in here. There's a minus cosine x, and you can see this right here is very easily simplifiable. You can simplify it. Minus integral of v minus cosine x du was the secant square x. Again, you can simplify this. You can cancel things out. If you had done u is equal to sine x and proceeded with that direction, you would have gotten more complicated integrands afterwards. From this substitution, it would not have helped you out. Tan x is sine x over cosine x. Multiplied by cosine x, you just get minus sine x because the cosine x's would have cancelled out. Here you have a minus, minus becomes a plus. Cosine x cancels out with one of that factor, and you just left with secant x dx. And your final answer after this, and you know I'm not forgetting this, I've just put it aside. This is easy. Minus sine x plus natural log secant x plus tan x plus c, but we are doing definite integration, so let's do this proper substitution over here of these definite intervals. We have pi over 6 and 0. You will have minus sine pi over 6 plus natural log secant pi over 6 plus tan pi over 6, and then we have the minus. Then we plug in the lower intervals. Minus sine, lower interval, minus sine 0 plus natural log secant of 0 plus tan of 0. You see how you're doing it? Upper limit first, expression, then minus, then lower limit. And then we plug away minus 1 over 2 plus a 30, 60, 90 here with the reference of 30 is going to be 1 root 3, 2. So natural log of this 30 angle right here, which is my reference, will be 2 over root 3. Tan will be 1 over root 3 minus, this is 0. Natural log of secant 0, cosine of 0 is 1, secant of 0 must therefore be 1. Natural log 1 plus 0. All of this zeros out because natural log of 1 is a 0. You're essentially just looking right over here. And that's all you have to solve. And it's not hard. Minus 1 over 2 plus natural log 3 over root 3 can be a good answer, or you can calculate and post a numerical answer. And the final area representing the area under the curve for that function from that interval 0 to pi over 6 is 0.0493, and that right there is a good answer. We ended this video with this third question because I'm trying to keep this video short and to the point with good practice questions. And here we're focusing on integrating by parts technique but looking at definite integration at the same time. We have two different dissimilar functions over here. X cubed is by no means a derivative of natural log x because only 1 over x is the derivative of natural log x. You have to make a good smart substitution here, and it will not be u equals x cubed because you'll complicate your entire integrand. The best substitution is u is equal to ln x, and you'll see why as you do this question. You can try it out yourself with an x cube and you see your entire integral will become harder, not easier. Du is equal to 1 over x dx, and v is equal to the integral of what remains, x cubed dx, which is x to the 4 over 4, you know, the n plus 1 divided by n plus 1. Now you put everything to this format, uv minus integral v du. U is ln x. V is x to the 4th all over 4 minus v is x to the 4th over 4, but I'm bringing this over 4 right out here. Nothing wrong with you doing that. Du is 1 over x dx, and this is why it helps out because this 1 over x dx, you can simplify it with this and make it an x cubed dx. So this integral v du boils down to x cubed dx by means of everything here in front of you. This is easy. You have x to the 4th ln x over 4, and you know we have everything here from an e to a 1, upper limit, lower limit, minus 1 over 4. Integral of that antiderivative is x to the 4th over 4, and then again from e to a 1. This x to the 4th over 4 times 1 over 4 is really x to the 4th over 16. We can eliminate some of this clutter and we can present this as our good answer. If we were doing an indefinite integration procedure, we would just put a plus c over here and we wouldn't have intervals, but this would be our answer. But this is a definite integral. We can calculate it and we'll continue with this procedure. I'll put e's in first, then I'll put 1s in places of x, and we'll do the difference of the two. It'll be e to the 4th ln e divided by 4 minus e to the 4 over 16. This is my upper limit placed in. Now you do the difference of that with the lower limit, which is 1. 1 to the 4th, ln 1 over 4 minus 1 over 16, which is just 1 to the 4th over 16. You know very well natural log of 1 is a 0, so all of this zeros out. Ln e is equal to 1, so you can erase that. You really have here on the top e to the 4th. What you have is e to the 4th over 4 minus e to the 4th over 16. This minus 1 over 16 is plus 1 over 16. And you could, if you want, present your answer as a fraction. 4 goes in 16 4 times. You could say 4 e to the 4 minus e to the 4 plus 1 over 16. You can say this right here is your answer, but I want to present a numerical answer, and I'll post it right here doing this calculation, which you know how to do. And it comes out to be 10.299, or you can say 10.3, and this would represent the area under the curve. You could either present this right here as your answer in a fractional form, or you can present this. They both should be good answers. And this right here is this question completed. So keep in mind the integral technique, integrating by parts, is an excellent technique, especially when you're looking at an integrand such as this, where these two are not having a clear relationship as a function and its derivative, for which polynomial substitution technique would work. Then you look at this technique, but technically this technique is more universal than that, because you can still do those types of questions which are normally handled with polynomial substitution procedure. You can still handle them generally with this, and this is just a very versatile and enjoyable technique. Leave any comments if you have any questions or concerns. Thank you for watching. Have a nice day.